Hello, my name is Brandon Earl, and this is my project for the exam replacement. So I was asked to solve 13.17, and from the problem we see that the system is at 343.15 degrees Kelvin. The natural log of the activity coefficient for 1 is equal to 0.95 multiplied by the liquid fraction of component 2 squared. You can also see that the natural log of the activity coefficient 2 is equal to 0.95 times the liquid fraction of component 1 squared. We're told that the saturated pressure for component 1 is 79.8 kPa, kilopascals, and the saturation pressure for component 2 is 40.5 kilopascal. We are going to assume the validity of equation 13.9, which is the modified Raoult's law, and we're asked to find the bubble pressure for the following conditions of temperature 343.15 kelvins and the liquid fraction of component 1 is set to be equal to 0.05. We're also asked in part B to make a dew pressure calculation, and we're given that the temperature is 343 and the vapor fraction of component 1 is equal to 0.05 as well. And then finally in part C we'll go on to find the azeotrope composition and pressure at the temperature of 343.15 Kelvin. The best way to start this off is we're going to list our knowns. So what we know to begin with is that the temperature is equal to 343.15 Kelvin. We know that there's an expression for the activity coefficient, which is the natural log of the activity coefficient for 1 is equal to 0.95 x squared, and this is x2 squared, so the liquid fraction of component 2. And there's a similar equation for the other activity coefficient. Except this one will be x1, so the liquid component fraction of component 1. We know that P1 set is equal to 79.8 kilopascals. And that the saturation pressure for number 2, component 2, is equal to 40.5 kilopascals. All right, what else do we know? So from part A, we are told that the liquid fraction of component 1 is equal to 0.05. And this is at our temperature up here. So we're going to start off this problem by using this equation right here. So this is total pressure is equal to the liquid fraction of component 1 multiplied by the activity coefficient for 1 multiplied by the saturated pressure for component 1 plus the liquid fraction for component 2 multiplied by the activity coefficient for component 2 multiplied by the saturated pressure for component 2. So what do we know from here? So we have x1, this is known. We have y1, which we can find. that's not erasing. All right, that'll I'll just have to do. We're given our saturation pressure. We don't know x2 yet. We have an equation for the activity coefficient for 2, and then this is a known. So this is what we have. We can find x2 if we use the simplified or generalized equation where the fractions of component 1 in the vapor plus the fractions of component 2 in the, or not the vapor, I meant to say the liquid, add up to equal 1. We can rearrange this so that x2 is equal to 1 minus x1. And since this is a known, we can find x2. What else do we have to do? So we have to rearrange our activity coefficients so that we can plug them in. So right now we have the natural log of the coefficient. And I'm just going to put, I'm only going to do this once just because it's the same strategy for both. So it's 0.95 multiplied by the opposite liquid fraction squared. So we're going to get rid of this natural log symbol right here. How we do that is we raise both sides exponentially. So it'll be 1. That's because natural log of something raised to the exponential cancels out, and you're just left with this right here is equal to 0.95 multiplied by x2 squared. If we were to go through this for the other equation, it would just be the natural log of the activity coefficient 2 is equal to 0.95 times x1 squared. So this is going to be a 1 here and a 2 here. That's the only thing that changes between the two expressions. So looking at what we have now, so we have this equation, we know this, we have something we can substitute in for this, we know this, we can substitute something in for this, same here, and then we know this. So we have everything that we need to find our total pressure, bulb pressure. So we'll go P is equal to x1, y, or gamma 1 multiplied by P1 sat plus x2 gamma 2 P2 sat. So x1, as we were told earlier in the problem, is equal to 0.05. Let me just double check. Yep, 0.05. This is going to be multiplied by our exponential substitution. the exponential of 0.95 multiplied by x2, but if you remember from before, we had the equation that x2 is just equal to 1 minus x1, so that's what we'll be substituting in here. I'm not going to write it out just for the sake of space, but if you take 1 and you subtract 0.05, you get 0.95. So to save space, I'm just going to cube this right here, because that would be equivalent. And then this is also multiplied by our 79.8 kilopascals. And now onto the second half of the equation. We have another x2, which is 0.95. We are going to multiply that by the other one of these, so it's exp of 0.95 multiplied by x1 squared, so that's 0. I'm running out of room. I'm going to put it right here. So ignore the 0 up here. So minus 0.05 squared. And then we're going to close the brackets on the exponential there. I mean parentheses on the exponential. And multiply by our other saturated pressure, which is 40.5 kilopascals. Once we plug this into our calculator, we find that the bubble pressure is equal to 47 0.97 kilopascals. And then we are also able to extend this on to find our vapor fraction for component 1. If we used equation let's see. If we use equation 13.19, we can find our vapor fraction. So y1 p1 or p is equal to x1 activity 1 coefficient and the p1 set temperature. So we're going to just simply rearrange this. So we have a known value right here. This one is also known. We can use our substituted expression here. And then this is as well also known. So we would get this expression if we isolate the y1. Remember, this value right here is equal to this right up here. I'm not going to write it just to save space. And then P is this right here. We're going to plug that in. So it's 0.05 multiplied by exp of 0.95 cubed multiplied by our saturation pressure for species 1, which is 79.8. I'll put a there we go. Kilopascals divided by our 47.97 kilopascals. And this is equal to 0.196. And it is unitless because our kilopascals here will cancel out with these right here. And it's a fraction as well. So that is part A of this problem. Moving on to part B. We're asked to find the dew point calculations, and we're giving y1 is equal to 0.05 and the temperature. So our knowns are the same as before, plus now we know, or we're asked to find it at this value. And then we're going to do it at the same temperature as part A. So we're again going to use our generalized equation of one is equal to x1 plus x2. So we're going to want to find a way to relate these values right here, but put it in terms of the vapor. So if we look back at equation 13.19, we had just used, so we said y1 multiplied by the total pressure is equal to x1 times the activity coefficient for component 1 multiplied by the saturation pressure for component 1. If we rearrange this, we can find a way to plug it in. So all we're going to do is divide by these two terms right here, and that'll leave this value open on one side, isolated. That's the word I'm looking for. And we're going to do this for both components. So I'm just going to put an I here. Which will make this one a little confusing, but we won't do that until we substitute it. So when we do the isolation, we get x to the I is equal to y to the I multiplied by the total pressure over the activity coefficient of species I multiplied by the saturation pressure for species I. So when we plug that in, we should get 1 is equal to y1. I need to find, oh, here we go. y1 multiplied by the pressure divided by the activity coefficient for species 1 multiplied by the saturation pressure for species 1. And we're going to add y2 multiplied by p over gamma 2 times p sat 2. So from here, we can see we have some values. These we can find, these we can find, but we have one known, one unknown, and a common numerator. So what we're going to do is we're going to pull this common numerator out from the equation, and we get 1 is equal to p multiplied by everything else. From here, what we can do is we can isolate each side. So the general idea of this is that we want to find where the pressures are going to line up. So we have this one right here, and then this essentially is pressure. If you look at the expression of, where is it? Yes, so we're going to get these evened out, and what that will allow us to do is evaluate the activity coefficients, and then we can plug this into Excel. Once our activity coefficients are going to line up with our pressure over here, then we know that we found the due pressure, which is what we're trying to find. So I'm going to take this term and put it under here. So you divide both sides by that value, and we should get P is equal to 1 over this whole expression. Now, what we will do is I'm going to take that expression and go over to Excel here. So as we see, we have 1 over y1 times the activity coefficient of 1 times the saturation pressure for 1 plus y2 gamma 2 p2 sat. And then, oh, one thing that I forgot to do is we're also going to break up our, I'll just click after. Oh, here we go. We're also going to break apart our pressure term. So I believe I said earlier that we knew this, but that is incorrect. We don't actually know this yet. So when you break this apart, we are also told that pressure is equal to the sum of species I times x to the I, activity gamma to the I, and pi sat. What this will allow us to do is plug in values here and evaluate these activity coefficients with the ones that we had up here. So we go to Excel. So this right here is the left-hand side of the expression, and this right here is the right-hand side of the equation. And as you can see, what I did here is I put in a bunch of x1 values. I initially started off with 0 to 1 at 0.1 increments. Once I got to this expression here, I could see that I had gone too high, so that meant that x1 was too large. So what I started doing was working down in smaller increments. I first did 0.25, this one right here. We can see the right-hand side of the equation is too large still, so then I had to go smaller. And that's when I started doing 0.005 increments. Once I finally got closer between these two, I split it in half, and these are very similar. It's not exact, but this is to the precision that I chose to go to. And we find that x1 is equal to 0.01045. So if we plug this into Raoult's law, let me insert a new drawing. If we plug this into Raoult's law, we can find the dew pressure. So the dew pressure is going to be equal to x1 activity 1 coefficient p1 sat, and this will be divided by our y1. So this is just the expression that we used earlier. In part A, to find the vapor fraction at the very end of it. But instead of moving this pressure down here, we're moving the y that was multiplied by down here instead. So our dew pressure is equal to x1, which is going to be what we just found from the Excel document, which is 0.01045. Our activity coefficient, so this is going to be for species 1, so that's going to be the exponential of 0.95 multiplied by, and a note is that we can't use the one activity expression from part A because our x1 has changed. I mean, we can use the expression, but we can't just use 0.95 cubed. And so it'll be 1 minus x1, which is 0.1045, and we're going to square that expression, not just this number, otherwise that would throw off our value, which is also multiplied by our PSAT, which is 79.8 kilopascals, and divide this whole thing by our vapor fraction that we were given in the beginning of 0.05. And then that's all that's left to do is to plug this in. So we have our dew pressure is equal to 42.28 kilopascals. There we go. So moving on to part C, we are asked what are the azeotrope composition and pressure for the following temperature. So we're trying to find the azeotrope, and the definition of azeotrope is that it means that the vapor composition is equal to the liquid composition. Another way of saying that is just that y1 is equal to x1. So to find this pressure, what we're going to do is we're going to use this expression. So the pressure is going to be equal to the activity coefficient of I multiplied by the pressure of I saturated. And since it's an azeotrope, we can just rewrite this as a 1. instead of an I, and put another equal sign here, and do gamma 2 P2 sat, because these will be equal. So in order to do this, we're going to sub in our expression for these two. This is a known, this is a known, and then we'll just have to find the x1 or x2, whichever way we choose, that satisfies this expression. So exp exponential of 0.95 multiplied by x1 squared multiplied by our saturation pressure. Oh wait, multiplied by our saturation pressure, which is going to be 40.5 kPa, kilopascals. Is equal to exponential of 0.95 multiplied by x2 squared. And then our P1 sat is going to be 79.8. So what I see here is that we have two saturation pressures, so we're going to want to isolate those to one side, and then we have these expression here. We're going to want to isolate those to the other side. So I'm going to divide this side by the exponential over here, and I'm going to divide this side by 40.5 kilopascals. And we do that on both sides. And what we end up with is 79.8 divided by 40.5 on the right hand side of the equation is equal to the exponential of 0.95 multiplied by x1 squared. And this is divided by exponential of 0.95 minus x2 squared. So one of the laws that we know from calculus is that when you have an exponential divided by an exponential, you can rewrite it as what's ever inside of this expression minus this one, all within exponential bracket. Another thing that we can do is simplify this. So we divide 79.8 by 40.5, and we get 1.97 is equal to exponential of, and I'm going to do this step right here. So it'll be 0.95 minus x1 squared minus, sorry, this is not a minus sign, this is a multiplication sign. I've probably been messing that up this whole time. So multiplied by that minus 0.95 multiplied by x2 squared. And from here, we can use our x1 plus x2 is equal to 1, sub in for this value right here, and we'll get 1.95, not 95, 97. is equal to exponential of 0.95 x1 squared minus 0.95 multiplied by 1 minus x1 squared. All right, and that's all that's left to do for that part. So we're going to use a solving calculator and solve for where x1 makes this expression true. So if we plug that into our calculator, we're going to find that that is true at x1 is equal to 0.8568 or 0.857. Then we want to find the pressure here. So the pressure at this point can be found using our x1, this expression, x1, gamma 1, p sat 1, plus x2, gamma 2, p sat 2. And that expression looks like this once we plug in our gamma substitutions and our x substitution. So we do know x1 now, so we don't have to keep guessing on that. I'm just going to write x1 even though we know it here, just to save space. Exponential of 0.95 multiplied by x2, or 1 minus this value right here, which is going to be equal to, I'll just write it out, 1 minus 0.857 squared multiplied by our 79.8 kilopascals. And this is going to be plus x, well, not x2, 1 minus x1 multiplied by the exponential of 0.95 multiplied by our 0.857 squared and multiplied by our P2 sat of 40.5 kilopascals. And when we plug in our x1 values into this equation, we will get the pressure of 81.37 kilopascals. And then the final thing for us to find is the vapor of component 1, vapor fraction of component 1. And since we know it's an azeotrope, it's going to be equal to x1. I'm going to call this x1 and y1, which is equal to 0.857. And that is how you solve part C. So that is the end of this solving presentation. I'd like to thank you. If you have any questions, please feel free to contact me. And have a good rest of your day. Thank you.